So this is the second part, photometry on stage 2 images obtained with NIRCam. In this case, we are using NIRCam simulated images obtained using Mirage, that is our simulator that is publicly available, and you can download it and run through the pipeline of the Large Magellanic Cloud LMC astrometric calibration field. So a sort of not, let's say, not that crowded, but not that sparse. So it's in between. Simulation are obtained using 4 points of pixel dithering for 2 couples of white filters. So in total 4, because as I said during my introduction, when you use NIRCam, you have both short wavelength and long wavelength observed at the same time. In this particular example, we will use only the one image for the short wavelength filter, so F115 and 200. But all the other, and only for one detector, NRC-B1, but all the other images, the 4 images for the different filters for this detector, and also for B5, that is the long wavelength detector, and the stage 3 image. First thing we want to do is the usual Python import. Just let me say a couple, we can run it twice, doesn't matter the warning. Just a couple of caveats about this, about 2 programs that we are using. One is JWPSF. If you install in your laptop JWPSF through Astroconda, the data files are already there. But if you're using PIP or you want to use the GitHub to download the development version, you have also to download the data, and you can find in the read the docs all the instruction for JWPSF and how to install it and download the data in that case. And then you have to point the environment. And the other thing is, of course, PySinfo, that is distributed separately, and in particular, the data files are distributed separately. And here there's a note on how to set up the directory where you want to put this file. This is not fundamental, it's just if you want to use stellar spectra when you create your synthetic PSF star. So we can go ahead, usual plotting function. And here is similar to what Mattia has done for MIRI, is also a dictionary for the PSF full width at maximum for NIRCam, obtained from the analysis of the simulated PSF from JWPSF. And of course, we will update those numbers as soon as we have the real one from sky observation. As I said, here I'm just analyzing one image because, let's download this, and in this cell, as you can see, I'm just downloading the image and checking that it's not already there, so we don't waste time downloading the image. And we are also extracting some information from the header, and in particular the filter and the detector. So we can run this cell, and I can go back to what I was saying, that in this particular notebook, I'm gonna show how to analyze each image separately, because I wanna give you an overlook of the different way we can create a PSF and build a single PSF and do the PSF, build an effective PSF or empirical PSF, and also how to do the PSF photometry. Of course, when you're analyzing multiple images, like for example in NIRCam, you have every time you take an observation, you have at least 10 or 5, depending if you're using both modules. You want to create some sort of loop and function that can help you analyze multiple images at the same time. So let me know if you were not able to download the images, and we are going to analyze one filter. The other filter is for the exercise. And the first thing you want to do, of course, is always display your image, so you have an idea if there are any problem, artifacts, and stuff like that. And this is the NIRCam image. As you can see, is a star field with a lot of stars, quite crowded, but not too much, like a center of globular cluster, of course. What I'm doing in this cell, I'm just converting back using a keyword that is in the image header, and also multiply for the pixel area map. So perfect. First thing we want to do today is creating a synthetic PSF using JWPSF. Probably you already heard of this package if you worked before with simulated data for James Webb, or if you just prepare your observation using the ETC. And here there's a bunch of, I'm not going to spend a lot of time explaining what WebPSF is and what it does, but there are a bunch of links where you can see the capability and limitation of WebPSF. And below, there's a function that allows you to create a single PSF or a grid of PSF, and you can save those as a FITS file. And we will see what we need to specify in this function to use WebPSF. So there are also other information here about the centering, normalization, and subspectrum. So if you want to know more, you can read it from the notebook, and of course you can check the WebPSF, read the docs documentation. So this is the function that we are going to use. The first thing, of course, you want to define the instrument that you're going to use, that is NIRCam, and the detector and filter, and that's why we extracted those information from the beginning. And then we have to decide the field of view of the PSF and the number of PSF if we are going to create a grid. So the field of view, it really depends on what you're interested. The more you increase the size, of course, the more you increase the computational time. So knowing that 80–90% of the circle energy for the NIRCam PSF is in 5 to 10 pixels, you want to limit your radius to that size. Of course, if you're interested also in sampling the wings at largest distance, you're going to increase your PSF size. And as I said, here you can create a single one or a grid one, and you can save it in a file if you want. You can see the commented part here is because I'm also, in this case, we are not using a source because we don't have the data files for PySynfot, but if you install it in your laptop, you can define a source inside the PSF grid function, and here you define what kind of spectral type you want for your source. And so here we can create our first PSF, the single one. So we can type and this create PSF model. I hope is right. Yep, create PSF model. What we want to do is define the detector, what filter we are using, the field of view, and we can have, like, say, 11 pixels. If we want to create a grid, so we want to create more PSF, a grid of PSF to account for spatial variation, and that, for example, is one of the things that you have to decide depending on what you're analyzing. So in this particular case, it's a single one, so we say false, and then the other thing is save PSF. Save PSF, yes. Save PSF if we wanna create a FITS file. So otherwise, we have stored the PSF in this PSF WebPSF single. But when you create more than one and you wanna check, for example, changing the field of view, you wanna probably also store your PSF. See, and here we are creating our first our single PSF. And we can display the PSF, so you can have a look of how is it the PSF for this particular filter. And here's the image. And now we can go and create a grid. So it's the same function, but we type create PSF model. Again, we define the detector, the filter. You can also type, of course, the filter that you are using, but it's easier since we already assigned. Sorry. Then the field of view. In this case, we want to create a grid, so we say create grid true, and then we have to define the number of PSF that we want to create. Of course, it must be a number that you can do the square root, and of course now we have firefighters, and then we have save PSF true. You have everything, yes. And see, now it's creating 16 PSF at fixed position, depending on the number, of course. You divide the array and you create the PSF at those 16 fixed position. It really depends on how much time you want to spend building this PSF. For example, now you have seen that to create 16, it took like 30 seconds, 1 minute, something like that. If you start to increase the size of your field of view, it's going to take much more time. The other thing is what you're interested usually is that you want to model the part where all the flux is in a star, right? So you have 80-90% usually that is inside a box of 10 by 10 pixel, more or less, depending on the circle energy. But let's say between 5 and 10, this is true for different instruments and also for different filters. So if you're going to do the PSF just inside, if you're going to measure, let's say, fit inside a box of that size, it doesn't really matter if you create a PSF that is much larger, right? But there are cases where, for example, you want to study the wings of your object. So you want to, for example, simulate what happens at a larger radius because you want to see how the wings behave or what percentage of the flux is in the wings, how can affect a faint source. That, let's say you have a faint source and a bright star closer, you want to simulate how the wings of your bright stars affect the faint ones. So in that case, you want to create a PSF that is larger. Great. So as we have done for the single one, we can show the PSF, and here there's the grid with the 16 PSF with the different position. And just to give you an idea, this is the difference from the mean. So you can see that depending on when you are on your detector, the PSF is different, the shape. Just to give you a better visualization, I just calculated in this cell that I'm running now, the difference from the single PSF that we created before, that is in the center of the detector, with one in the corner. So you can see that there is a 1%. That's not a lot, but still there's a 1% difference between PSF in the center and PSF in the corner. And so this was the first part. And so now, if you want to do the PSF photometry, you can do it with the synthetic model of your PSF. Another thing you can do, of course, is build your own empirical PSF. So what does it mean? It means that you're going to measure, you're going to create the PSF using the stars that are in your field when you observe. Of course, you can do it only if you have enough stars, so it's really science-driven, this particular option. And to do so, we are using, I forgot to mention, we are using PhotoTools for that part of the notebook as Mattia did for the Aperture one. So those are other functions inside PhotoTools that you can use to build your empirical PSF. So building an empirical PSF is mainly this is a very basic example, but there are 3 steps. So you need to find the stars that you want to use to build the PSF. You want to select which one in particular, because you don't want to use stars that are contaminated from the wings of others, from the flux of other stars. You don't want to use the stars that are too faint, because of course they are more uncertain. And once you have done all this, you can use ePSF to build your final empirical PSF. So the first thing we do is finding the stars. I'm not going to spend a lot of time on this cell below, because of course Mattia already explained really well what does it mean the MMM background, the function to calculate the background, and also the function to find the stars. So we just run this cell. As you can see, is a simple background, or if you want to do something more complex, you can just change here to true, and you use the background to the instead of a simple MMM background. Then, and we return the data background subtracted and the standard deviation, so you have the image and also an idea of what is the standard deviation of your background. And then, as Mattia explained, also in my case, I'm using the star finder. So here's the function. What you need to define is just the threshold, and the full width maximum is defined again with the PSF sigma, or full width maximum, that we are extracting from the dictionary that I showed you before. So here, let's just write this function. So it's find stars. We need the detector. This is just, you don't really need a lot of, you don't really need it to do it, but it's just when you're analyzing multiple images, it's useful to print what you're actually, what the catalog that you're obtaining, where it's coming from. So, and also is important because the filter is associated to the actual full width and maximum that you are using. And the threshold is not really important here to go deeper because we are not looking for all the stars. We just want to have a good number, and then we're going to select which one we want to use for our effective PSF. And as I said, the background can be false. Okay, so as you can see, we found like 8,100 something stars, so a lot of them. And of course, you don't want to use all of them to do your empirical PSF. So you can select the sources. There are many ways to do it. So we are doing this in a plot. So first thing, we just plot the magnitude that, as Matthias said, is not a real magnitude, but it can be helpful to discriminate between faint and bright, and these two parameters, that is sharpness and roundness. So for example, here you can see that we have enough stars, so we can say, okay, let's just stop at -4. So we set here the mag limit -4. And let's go back and look, and we can say, okay, let's try 0.8 and 1, and we can refine it later for the sharpness. So you put 0.8, and 0.75 and 1. And just we uncomment this. And for the roundness, let's take a look. Let's start with 0.5 and -0.5. Okay, rerun the cell. And as you can see, well, we still have a little bit of room in the sharpness, and also about the upper and lower limit, and also in the roundness. So let's do something like this. I already have this value tabulated, and that's good. 0.78 and 0.92 for the sharpness, and let's do 0.4 and 0.4 for the roundness. Okay, perfect. So now we can create the catalog of selected source. Another thing that you can do, of course, that I mentioned before, is that you don't want to use stars that are too close to each other, because, of course, they are sort of cross-contaminating. So here in the cell below, I also included the possible separation criteria. And as you can see, the first thing, we just mask with the parameters, the limit that we choose before, and we have the first catalog. If you want to be even more conservative, you can include this separation criteria, and you can say that you don't want, in this case, I'm using 10 pixels, you don't want any star closer than 10 pixels. Independently of the magnitude of the star, it can be brighter or fainter, but you don't want any star closer than 10 pixels to the one that you're selecting, and can be 10. And it really depends on the number of stars that you have in your field, and also on the crowding of the stars. So we can run this cell. And as you can see, we have 850 for without any minimum closest neighbor selection, and 659 using that particular criteria. Perfect. So now we have our sample of stars that we can use to build the effective PSF. And to do this, we just use this function that is ePSF Builder. If you want to know more about it, you can click on the link. And what it does is basically extract cutouts of the stars, and then using the size to determine the parameter of this cutout. And then it creates, iterating a model of the PSF from all these cutouts that you have. So it's basically using 850 or 650 stars to create a final model of your PSF. empirical PSF, of course. Just a note here, we are limiting the number of iterations that ePSF is using to 3 because we don't want to have a lot of time in this webinar, but of course you should use 10 or more. And here I'm just using the main parameters, but of course if you click on the link and you follow what is in the ePSF, you can see that you can define also other things in the function. So one thing, of course, that we want to do is also, as you can see here, we are going to mask the objects that are too close to the edge. So perfect, we can build the empirical PSF. So we said is build ePSF. We're doing, as usual, detector and filter. And then the size, we're going to keep 11. The found, we need to provide the table of stars where the cutout is going to be done. So because it needs the X and Y position. And so it's like found stars cell. I'm going to use, as I said, only the one, the less conservative approach. So I'm not using the one with the separation criteria, but you can try. And the other sample here, I have it. That's why I should also there. Is 4 again. And the iteration we said is 3. Now is iterating, is creating empirical PSF, and we can display our empirical PSF. And that's it. As you can see, it is again 11 times 4. And there's also a column and a row added at the end. So the center of this of the empirical PSF that we created is not on the crosshair of the array, but is in the center of the pixel. Perfect. Now we have created our synthetic PSF and empirical PSF, and we can do PSF photometry. And as I said, this is the most straightforward and basic way, but just to give you an idea of what we have right now in terms of tools and what you can already do with PhotoTools and with this notebook and packages. So to do the PSF photometry is very similar to what, again, if you're used to what Setsan coded in DOFOT, is very similar. So it's basically finding the stars, grouping them, measuring, subtracting, and repeating the process if you're using an iteration. Otherwise, if you're using just the basic PSF photometry, you don't have the iteration part. The difference between basic and DOFOT is that the first one, you can implement your own algorithm for some of the things that are inside the PSF tool, while DOFOT is more related to what is already in the old version of DOFOT. So here I'm just, and that's a good thing about PhotoTools in this particular case, is that you can just plug in your different tools to do the finding, the grouping, the fitting, and also the model of the PSF, and PhotoTools is able to recognize those and do the PSF. There are a couple of things that I want to mention. Of course, one, we discussed the finder. We are going to use the Star Finder. The group maker, we are going to use the EO group. If you're not familiar with the EO group, again, it comes from the DOFOT, as the name says. And that's just the idea that, of course, you want to divide the entire list of stars that you found in the groups of mutually sort of overlapping stars. So, of course, there are stars that influence each other when you do the profile, as we've seen, for example, in the presentation when I was showing the image of the two stars close to each other. And the size of this group, it really depends on the crowdness of your field and also on how much time you want to spend on computation. Because if you increase the size, of course, you have to fit multiple stars at the same time, so you increase the complexity of your reduction. At the same time, if it's too small, it means that no other stars influence what you're doing. So it's a trade-off, and of course it's part of what you learn when you do PSF photometry. You go back and forth and you double check your results. Then you include the filters, of course, the algorithm that you want to use to fit the sources, and we use the AstroPy filter, this AstroPy filter, the number of iteration in which the loop is done, and the shape in which the fit is done. And that's why I was using, and that's part of what I was telling before about the size here, is the shape that we use to compare the data with the model. So if you create a PSF that say with the field of view of 100, but then the fit shape is only 11, it doesn't really matter what you have outside of the 11 pixel of your PSF. And then as the aperture radius is just to compute an initial estimates for the fluxes of the source. Here I combine again everything in a function, and there's the filter. I'm calling the background, so I'm doing this is the function for the finding. The grouping I'm using 5 times the PSF full width maximum, but of course it's something that we will have to check and refine when we have actual data from Sky. The model of the PSF, and this is actually the routine that does the PSF. So as you can see, we are using the finder.find, group maker, the group, our background, the model of the PSF, the model of the filters, how many iteration, and the fit shape. And then here, as before, when we were doing the PSF, in my function, you can decide if you want to save the residuals as a fits files, and also if you want to save the output as a table. So, okay, we are ready to run the PSF photometry. One thing, since it takes between 10, 15, 20 minutes, depending on the number of sources, of course, and the threshold that you are selecting to run the PSF on the whole image. Here I'm just using a cutout just to give you an idea of the code that is running and working. So we are just taking a 500 by 500 pixel area of the image. And we are creating this two directory just to store our output and our residual image. And we can write the PSF function here. So PSF what? Data is equal the one that we just defined. As usual, detector. Filter. Then the threshold, let's say 10. PSF model, in this particular case, we can use the grid, but you can use the single one or the empirical PSF that you just created, just to have an idea of how the code works. And then let's say save residuals. Yes, we want to save a fits file and also save output true. Okay, so now it's running. It should take 1 minute to do. Okay, so we have performed the PSF photometry. As you can see, the number, of course, is really low because we are using only a small portion of the image. And I just want to show the photometric output catalog. And here you have XY position, the original one from the find, and the one from the PSF fitting. And then if you want, when you are, you can use this notebook to compare this position also with the input one to learn how the PSF is definitely better, as Mattia was mentioning, because you get the astrometry for free, and then the flux, the parameter that I used before, uncertainty for the flux and the position, and with iteration we detected the star of the object. And so now we can display the residual image. Yeah, and so disclaimer, I already done the reduction for the whole image before doing the webinar, so you can have a look at the whole image reduction. So now what we are doing is I'm showing the residuals for the reduction that we done 20 seconds ago, and I'm also downloading the residuals for my reduction on the whole image. So we can run the cell. So now, as you can see, we are downloading those. And here, as you can see, is the one that we have done. Now 500 by 500, and the whole image. As you can see, there are. It's a good job, but of course there are saturated stars where it's complicated, and other objects where the reduction could be improved. But all in all, it's a good job. And here is just the exercise. It's basically redo what I've done, but using the other image and the other short wavelength filter. Or as I said, I will put the link for also the long wavelength. So if you want to do the same things with the long wavelength, and otherwise in the solution notebook is already the cell are already populated. So I just want to quickly show the last couple of things. And let's say that we did the exercise. You have the reduction for both your 115 and 200. So I just want to show your first NIRCam CMD. So as I said, I did the reduction before. So here I'm just downloading here the two output catalog obtained with the WebPSF grid in this particular case. And I'm just perfect, downloading one, downloading the other, and transforming in Qtable. It's not that relevant, but yeah, perfect. We talk about the cross matching, so I'm just skipping through this cell, but what basically I'm done. I'm associating Radek coordinates to the x and y of my image on both the 115 and 200 filter. And then I'm just combining the two images using match coordinates sky, and I'm assuming that the object is associated from one filter to the other if the separation is less than half a pixel. So, and here I'm using the AstroPy units. So 0.5 pixel, as you know, the pixel scale for NIRCam is 0.031, so it's half a pixel. So let's match. And we have 7,000 and something in common. So now I'm just gonna load the input catalog so you can have an idea if what we did in our reduction is good or not. Of course, this is, as you can imagine, is sort of cheating because we are using Mirage, and so we are using WebPSF stars as simulated objects, and we are using the same PSF to do the reduction. But still, it's important to understand if the pipeline is doing a good job, and also if the program is doing a good job. So I'm just downloading the two input catalog that I use for Mirage. And we cross-match those two input catalog in the same way as we have done a couple of cells above. Perfect. And then I just want to show you the final calibrated, well, the input is calibrated, the output, of course, is not calibrated. And you can, as part of this notebook, to calibrate the CMD here on the right, let's call it instrumental. So if we don't care about the magnitude, because of course the left is calibrated, right is not calibrated, you can see that we did a pretty good job in our reduction. Of course, here at the bottom, as you can see, this one is there's a cut to the selection that I've done in the LMC astrometric catalogs, but and here there's no cut, but because that's part of the uncertainties when you go faint. Last thing I want to show is, okay, we created an empirical, single empirical PSF, but let's say you want to create a grid as you have done with WebPSF. So below here, there's a couple of functions that I included in the notebook that allows you to create also a grid of effective PSF. What does it mean? It's just a function that use all the ingredients that we described above. So finding the stars, selecting those, building the ePSF, and then depending on the number that you input in the function, decide how many empirical stars you want. So, but then your question could be, okay, but how can I decide what's the size my grid? So how many PSF how many PSF stars do I need to create X n PSF? So that's a good question. It really depends on a lot of factors. So it really depends on the number of sources in your images again. But what I've done here is just creating a count stars, let's say, grid function that allows you to basically start from this number that creates a 5x5 grid and de-escalate through till a 2x2 grid. So you're gonna create a 5x5, 4x4, 3x3, and 2x2, and you're gonna have an output of images where you can have where there is the number of good, let's say, stars in each of these cell, and also is written here as an output. You can define the minimum number of PSF stars in the output. So in your image, it's gonna be add if it's not enough. And in the, as you can see, we can run it this cell. In the output, it says not enough stars in the cell. So what you can do, of course, depend how many stars you want. You can increase, decrease this number. You can change the parameter of your finding. So if you remember, we selected only the one with magnitude lower than -4. Let's say you don't have enough stars, you can play with those parameters. But this particular case, as you can see, we have a 5x5, 4x4, 3x3, and 2x2. And 3x3, we have, let's say, a mean of 100 stars. You can see here all this number, 100 stars. And it's actually only the 2x2 with the selection that we did in the past that is pretty good, where we have 200 or more stars that you can use to build the PSF. And this is one of the images I was talking before. So if you go in figures, you will have 4 of them with all the different grid size that we created. So let's say that 2x2 is your choice, and this is just a function similar. It's just a function that creates the PSF, the effective PSF using all the ingredients that we discussed above. You can use this function also for the single PSF. As I said above, I just wanted to unpack everything so it was clear what we were doing. But in principle, you can create a single PSF. Actually, we can just do it. And here in this case, is creating a single PSF and is using the 800 plus stars that we mentioned above. Takes a little bit, and this is your PSF and where it's centered. But let's say, no, I want to create a grid of empirical PSF, and 200 in each cell is fine. So you can just put 4 here. And there are again a bunch of parameters if you want to save the output and the figures. That should be save a PSF, sorry. The save is not very intuitive, but as you can see now, it's similar to what WebPSF does, but it just says the coordinates and the number of stars in its set, and they are plotted here. And so, of course, as you have seen before, WebPSF can go to the corner because it's a synthetic model. In my case, we cannot go to the corner, so we have to take the center of the grid of the cell. And here are the 4 different PSF that we created for the grid of empirical PSF.